For years, Kubernetes had a standard way to route a web request by its hostname or path. But the moment your application spoke raw, TCP or UDP, that clean portable story mostly stopped. You could still expose the workload. That was never impossible, but you often had to choose between a plain service and a controller-specific extension. Then Gateway API version 1.6 changed the boundary. TCPRoute and UDPRoute became stable. Standard AP is. So what exactly became standard? And when should you actually use it? Let us remove one common misunderstanding first. Kubernetes services have supported TCP and UDP for years. A node port or load balancer service can expose a database, a game server, DNS, or another non-HTTP workload. The missing piece was a portable routing model around shared gateway infrastructure. Ingress did not solve this. Ingress is designed for HTTP and HTTPS. It understands web concepts such as hosts and paths, but it does not standardize arbitrary protocols and ports. Different ingress controllers often added their own TCP or UDP configuration. One controller might use a config map, another might use an annotation, another might define a custom resource. That can work. The problem is that your configuration now belongs to that implementation. Move to another controller, another cloud, or another platform team, and the same intent may need to be rewritten. Now, when we say layer 4 routing, we are talking about transport level traffic. For TCP, the gateway receives a connection on a known port and forwards that byte stream to a backend. For UDP, it receives datagrams on a known port and forwards them to a backend. The gateway is not looking for an HTTP path like /checkout. It is not reading a host header, and plain TCP route is not using a TLS server name. Its useful information is intentionally small. This protocol on this listener and port goes to this backend. That small contract is important. It is what makes the behavior portable across very different implementations. Gateway API separates the configuration into a few objects. First, a gateway class identifies the controller and the general kind of gateway infrastructure available in the cluster. Then a platform or cluster operator creates a gateway. The gateway owns addresses and listeners. A listener says, for example, accept TCP on port 12,340. The listener can also limit which kinds of routes may attach and which namespaces they may come from. Finally, an application team creates a protocol-specific route. That route points to the gateway and then names its backend service. This separation is not just tidy YAML, it separates responsibility. The infrastructure provider controls the implementation, the cluster operator controls the shared entry point, and you as the application owner control where your application's traffic goes. Both sides must agree before the attachment becomes active. Let us trace one TCP connection. A client connects to the gateway on port 12,345. The gateway has a TCP listener named database on that port. It allows TCP routes to attach. Your TCP route has a parent reference to that gateway. It uses the section named database, so it attaches to that specific listener. Inside the route rule, a backend reference points to a service on port 6000. The gateway controller watches these resources. It checks whether the route is allowed to attach, resolves the backend, and programs the actual proxy, load balancer, or network data plane. The YAML is the desired state. Packets do not travel through YAML. Once the configuration is programmed, connections arriving at the external listener are forwarded toward the services available endpoints on the backend port. Using a listener name is useful because the application route does not need to hardcode the public port. The operator can change infrastructure details while keeping a stable attachment name. UDP route follows almost the same model. The gateway listener uses the UDP protocol. The UDP route attaches to that listener. Its backend reference points to a service and port. Now, UDP datagrams arriving on the listener are forwarded to that backend. This covers workloads such as DNS, voice traffic, game traffic, and telemetry, where HTTP routing rules are simply the wrong abstraction. The similarity is deliberate. Once your team understands one gateway listener route and service relationship, the control model transfers across protocols. In Gateway API version 1.6, TCPRoute and UDPRoute moved from the experimental channel to the standard channel and received the version 1 API. Their older version 1 Alpha 2 forms are now deprecated and are planned for removal in a future release. But standard does not mean built into every Kubernetes cluster. Gateway API is distributed as custom resource definitions, and you still need a compatible gateway controller. It also does not mean every controller supports every route type. Before using this in production, check the supported features reported by your gateway class, then check a conformance report for the controller version you actually run. After applying the configuration, inspect both root and gateway status on the root. Accepted tells you whether the controller accepted it. Resolved refs tells you whether its references are valid. On the gateway, program tells you whether configuration reached the data plane. A YAML file being accepted by the API server is not the same as working traffic. This standard is useful because it stays small. TCPRoute does not promise payload inspection, address-based matching, idle timeout behavior, or client IP preservation. Those concerns are outside its minimal portable contract. There is another important limit. HTTP can share one listener because requests carry discriminators such as a hostname or path. Raw TCP and UDP do not provide a comparable discriminator to these routes. So one raw listener can effectively send traffic to one winning route. If multiple routes attach, precedence selects the winner. For 3 intentional TCP applications, you normally give them separate listeners and ports. And remember the surrounding pieces. The route still points to a service. Network policy and firewall rules still control allowed connectivity. Workload readiness still matters. Observability and exact load balancer behavior still depend on the implementation. Gateway API standardizes intent. It does not erase the data plane underneath it. Here is the rule I would use. Start with the information your gateway must inspect. If you need HTTP host, paths, headers, or request filters, use HTTPRoute. If you need gRPC aware routing, use gRPCRoute. If you need to route encrypted TLS connections by server name, use TLSroute. If the gateway only needs a TCP or UDP port and a backend, use TCPRoute or UDPRoute. If you are exposing one simple service, pause. You may not need shared gateway infrastructure, delegated route ownership, or portability between gateway controllers. In that case, a load balancer service may still be the simpler choice. That is the real significance of version 1.6. Kubernetes could already carry this traffic. Now, Gateway API can describe the routing intent with a stable, shared vocabulary. Use the richest protocol model you genuinely need, but no richer. That keeps your configuration understandable, portable, and easier to operate.